Computer Science Principles, Digital Information Review 1B. The previous one, we went over what is computer science, why would you study it, things like that. Now we're going to look at digital information. In this review, you will understand how binary is used in computer programming languages. You will be able to convert between binary, decimal, and hexadecimal representations. I will do a quick review of hexadecimal, but it won't be on the test, nor will it be on the AP exam. However, just going to throw it out there very briefly so that you can take a look at it, just in case you go into computer science, because you will probably need to know about hexadecimal. You will also understand how characters, sound, and images are represented inside a computer, and you will compare data compression algorithms. And when I say compare them, in a very generic sense, not in detail. Now, for the first lesson, we're going to look at binary, decimal, and hexadecimal. Binary. The binary number system is a base 2 number system where all numbers are represented using 2 digits, 0 and 1. Inside a computer, this is how all information is represented because of a computer's use of circuits and logic gates. 1 represents a circuit being open or on, and a 0 represents a circuit being closed or off. Here we have computer languages. There are low-level languages, machine language. There are middle-level languages called assembly language. And then high-level. That's what you're going to use. Very, very few people ever program in low-level anymore. And mid-level, again, it's a very small group that may do that. Okay? Over on the right-hand side here, you can see where we have high-level language, C, C++, Java, and this is what it would look like. Looks like a regular arithmetic statement. Assembly language, add A, comma B, tells you to add those two together. This one doesn't look so different, but when you do things like store things in registers or move bits around, assembly language starts looking a little more detail-oriented. Machine language, well, that's where you take this assembly language and change it into bits. And then, of course, we have the hardware that everything works on. Now, binary is the lowest level in the language hierarchy. This is the only language that computers understand and communicate in. A bit is a single 1 or 0. It comes from the contraction of binary digit. Byte is a group of 8 bits. Byte was used to refer to groups of 8 bits that a computer system was processing because it could byte off 8 bits at a time. The spelling was changed to B-Y-T-E instead of B-I-T-E so that you didn't confuse it with a bit. It was a little more distinguishable. Now, the other thing that I will mention is as we go through this, you will notice the words that are in blue. The words that are in blue are where you have blanks, where you need to fill things in the review notes. Okay? Now remember that those review notes you may have to turn in for remediation to show that you have gone through all of this prior to doing a retake. So anytime you see the blue, you may want to pause the video, fill it in, and then listen. Abstraction. This is the process of reducing complexity by focusing on the main idea. By hiding details irrelevant to the question at hand and bringing together related and useful details, abstraction reduces complexity and allows one to focus on the idea, on the big problem. Bits are grouped to represent abstractions. A single bit doesn't mean much, but when you put it all together, it becomes something more. These abstractions include, but are not limited to, numbers, characters, and color. There are many number systems: decimal, binary, hexadecimal, octal, quaternary, etc. And they all have their various uses in computer systems. In these notes, we will discuss how to translate between decimal, binary, and very briefly, hexadecimal. Base 10. This is the number system that is referred to as decimal and has 10 digits, 0 through 9. Humans across the world typically use base 10, probably because in the early days we had 10 digits. We had 10 fingers on which to count. We can represent every number we can think of with our 10 digits, 0 through 9. And why is it base 10? Because every digit or every place is some number of that base 10. So 1,376 is really 1,000, which is 1 times 10, our base, cubed. 300 is 3 times base 10 squared. 70 is 7 times base 10 to the 1. 6 is 6 times base 10 to the 0. And if we had decimals, those would be times 10 to the negative 1, 10 to the negative 2, etc. This is where we get the term base, because that is the value raised to a power which indicates the place value of each digit. Base 2 number system is referred to as binary and has two digits, 0 and 1. We can still represent every number with just 2 digits. Each digit is a placeholder, like the decimal representation above. It is just that the base number is now 2 instead of 10. Now, we have 1, 1, 0, 1. This is 2 cubed, 2 to the second, 2 squared, base 2 to the 0. Notice we always start, the 1's location is your base to the 0. And then you add all those together, okay? And I didn't include this one because 0 times anything is 0. That's why there's only 3 things added together here. Now, note, to differentiate between 1101 and the binary 1101, we use subscripts to indicate the number system 1376, or 1376 base 10, and 1101 base 2. Additionally, we also know that 1376 has got to be at least base 8, because base 2 only has 1s and 0s. Now, here we have the binary positions. Here's the first, second, third, etc. And this is the base with the power. And this is the decimal representation of each value. So if we want to know the largest number we can hold in 1 byte, that would be 8 bits. That would be 8 ones. Well, that means that we would have each one of these values and add them all together and get 255. Now, that's the largest value we can store, but we can have 256 numbers. Why 256 numbers and the largest is 255? Because 0 is a number. 0 through 255 represents 256 numbers or values. Now, let's look at binary to decimal conversion. Here's that table printed off again, and you only have to fill it in once, by the way. If I want to convert 0001, 0101 to decimal, how would we do it? I'm going to show you this one and then ask you to try these next two. Here, we have 2 to the 0. We have one of those. We don't have any 2 to the firsts. We do have a 2 squared. We don't have any 2 cubes. We have a 2 to the 4th, no 2 to the 5ths, no 2 to the 6th, no 2 to the 7ths. Now, 2 to the 1st is 1. 2 squared is 4. And then 2 to the 4th is 16. 16 plus 4 plus 1 is 21. Now, at this time, if you haven't already, pause the video and try converting these two binary values into decimal. Go ahead, pause the video. Okay, you're back. Did you get 53 and 87? Great. Now, what about, whoops, let me pause this. What about when you want to go decimal to binary? Well, decimal to binary gets a little trickier. So let's first look at 70, okay? What we do is we take the value, the decimal value, and divide it by 2. And then we write down, okay, here, we're going to write down the quotient. 2 goes into 70 45 times and has a remainder of 0. So you write both of these down when you're working through it. Then we take 45 and divide it by 2 and write down that it goes in 22 times with a remainder of 1. Then we just take the 22 and we divide it by 2 and we get 11, remainder 0. And we continue until we get down to the fact that 2 will not go into 1. So we get a 0, and then we have our remainder 1. At this point, we start from the bottom, okay? So we start with our 1 here, and then we work up. So we get 1, 0, 1, 1, 0, 1, 0. This is our base 2 or binary number that represents 70. Okay, so this takes a little bit of work, but obviously any odd number, okay, every odd number is going to give you a remainder of 1, and every even number is going to give you a remainder of 0. But now go ahead and try converting 101, 193, 204 from decimal to binary. Pause the video, try this now, and then restart, and then start the video again and check your answers. You're back. Did you get 1100101? What about these two? At this point, you're going to want to pause your video and check your answers. If you didn't get the right answer, go back and look. Did you just maybe, not write down the right number? In class, if you show your work and you accidentally leave one of these out, I can go back and see, you got it. If you don't show your work, I can't tell. Okay? Now, hexadecimal. This is going to be very brief. Base 16 is our hexadecimal number system, and it's referred to as a hexadecimal, and it uses 16 symbols, 0 through 9, and then A through F. We use A through F because we don't have any more digits past 9, and we have to go all the way up. We need 16 digits for base 16. As hexadecimal saves space, either paper or screen, you can more efficiently use hex instead of a large number of ones and zeros to represent binary. Keep in mind that hexadecimal is not a form of data compression, nor is it a language that computer reads. It is simply a different view into representing numbers. Now, okay, so now we're going to do decimal to hexadecimal conversion. So you're going to do 290 base 10 into hex. How do you do that? Let's take a look at the first one. And it's similar to going from binary to, or from decimal to binary. But let's take a look at it and see. Remember, we divided by 2 before, so guess what we're going to do now? We're going to divide by 16. And again, we have how many times and the remainder. How many times and the remainder. And again, the number of times gets divided by 16 again, and we keep going until all we're going to have is remainder. So here, 290 base 10 is 122 base 16. Okay, now that's all well and good. I'm going to show you one other one, only because this is not something you have to do on your exam this year, but it is a huge part of computer science, and so most of the computer science teachers aren't exactly sure why they took this out. Let's say we have 192 base 10 to go to hex. Okay, 12, remainder 12. And here's a 0. Well, this means that what I'm going to want to do is write down 12 and then a remainder 0. But 12 is 2 digits. Remember, each place can only have a single digit. So up here, I notice that when I'm in base 16, I use C. And that's where that C came from. The C is the 12. Okay? The C is the 12 and then the 0. So out here, I could even write C, 0, and again, keep going up. Now, go ahead and pause the video and try doing 590 base 10 to hexadecimal and 48,879 to hexadecimal. And are you back? Let's take a look. Did you get 24E base 16? Remember 14? You can come back up here. 14 is E. Anytime you have 2 digits as your remainder, you've got to go and pull a value from the alphabet. And here we go. We wind up with beef. Chicken, eat more beef. Or the cow tells you to eat more chicken. Okay, hexadecimal to decimal conversion. Just like when we did binary to decimal. Okay, it's the same kind of process, except with hex values. So if this is 192, I'm going to do 2 times 16 to the 0, 9 times 16 to the 1, 1 times 16 squared. So it looks like this. And then I'm going to add each of these items together. Okay? And again, 16 to the 0 is just 1. Okay, whoops, actually I had that times 2. Oh yeah, times 2, there it is. Okay? Sorry, the 1 was out here. Now, doing the same idea, try converting ABC to E4D and coffee from hexadecimal to decimal. Pause the video, try it, and then start the video again. Did you get 2,748, 11,853, and 12,648,430? Notice this was a little bit long, so I had to kind of dub it up there. If you struggle with some of this, you can pause the video and look at the work. Compare your work to this. Check to see if maybe you did a fat finger disease where you pushed the wrong button in the calculator, or maybe you just missed a 0 or something. Okay? All right, signed numbers. Binary digits can represent not only whole numbers, but also other forms of data. For example, to represent signed integers, we can use the leftmost bit of a number to represent the sign. 0 meaning positive, 1 meaning negative. The remaining bits are used to represent the magnitude of the value. For example, to represent the quantitate, -49, in sign and magnitude, we could use 7 binary digits with 1 bit for the sign and 6 bits for the magnitude. Right here, the 1 tells me it's negative, and then 110001 translates to 49. But how does the computer know that this is the number -49 instead of 113? Because if you counted that 1 as just another value, it would be 113. Well, the computer actually doesn't. A sequence of binary digits can have many different interpretations, and there is no fixed predetermined interpretation given to any binary value. The meaning of a binary number stored in memory is based solely on the context in which it is being used. Now, this might seem strange, but we have it all the time in the English language. Ball. Are you talking about a round object, a toy that you play with? Are you talking about an elegant party? Are you talking about having fun, having a ball, having fun? Which interpretation is correct? Well, if you just say the word ball, you don't know. We cannot say without knowing the context in which the word is used. Decimal numbers. How can numbers with decimal points be represented in binary? Well, the most intuitive way might be to first treat the number as a whole number, and then always insert a decimal point at the same point in its decimal equivalent. Consider the following 32-bit representation. I'm not reading off ones and zeros. And this converts to this number. If the context tells me that the above number is supposed to be a decimal at a fixed point, the 1/10,000th spot, meaning I have 4 decimal places, I can always insert the decimal here. So now I have 375,428.7045. Now this assumes that the number is always represented to the 1/10,000th in precision. But that's arbitrary. We could have chosen any different number of decimal places. However, we would need to choose this number beforehand, and it would apply to any number we encoded with this representation. This is called fixed point representation because the decimal point is always in the same place. Fixed point decimals are not great. They are very limited in the range of values they can represent. In our example with 32 bits, we could encode 0 through 429,496.7295. Seems like a fairly large range, but we couldn't even encode 1 million using this 32-bit 4-decimal place fixed point representation, and that's a problem. Therefore, we have floating point. Floating point numbers are used in most modern computers. Floating point representation means that not only is the numeric value determined by the binary representation, but where the decimal point is located is encoded as well. Note that moving the decimal point allows us to encode a much wider range of numbers than we could with fixed point representation. Using 32 bits, we can encode positive values from 1.17549 times 10 to the negative 38 to 3.40282 times 10 to the 38, or this many numbers. Now note the number of zeros in each. We cannot encode all the values between these two numbers, just values to a certain degree of precision. And we'll talk about precision error later, but understand you can't necessarily represent them all with just the 32 bits. To represent text in binary, the system assigns to each printable letter or symbol in our alphabet a unique number that stores that symbol internally using the binary equivalent of that number. ASCII, American Standard Code for Information Interchange. This is what was used for many years, and the table that follows outlines a common set of conversions established by converting between binary and alphanumeric characters. Fantastic. You have this table in your notes that are provided with this video, and you can look at it. You certainly don't have to memorize it. Know that it exists. Know that it was the original to encoding text, alphanumeric text characters. Now, to store the 4-character string fun in memory, the computer would store the binary representation of each individual character. So F, U, N, and exclamation point have the following byte definitions. As mentioned earlier, the only way a computer knows that the 8-bit value represents an exclamation point and not the integer value 33 is by context. Now, it is important to remember that not all languages are represented by the same 26 symbols that comprise the American English alphabet. The Greek alphabet is only 24. I have no idea how many are in the Japanese alphabet and some of the others. Not to mention, they don't even use the same types of letters. With this narrow bias, ASCII failed to provide for the many letters and characters that are common to the world languages beyond English. In order to make room for more symbols, more bits are needed. How many are needed? Quite a few. The current solution is to use Unicode standard. Unicode is a binary encoding system that can represent much more of the world's text than ASCII can. Unicode allows computers to represent most of the world's languages, alphabets, not just English. It uses a 16-bit representation instead of the 8-bit representation. Now, at this point, I'm going to stop this video, and the next one, I'll do this in 2 parts so that each one is only about 20 to 25 minutes long. So next we'll come back and we'll start talking about data in the next video.